All right, so now we move into Unit 3, the polynomials part of our final exam review, and we're going to go through a bunch of factoring and what a monomial, binomial, trinomial looks like, degrees of polynomials, all these really important concepts that come up through this. So let's start off with the first question here, which says, consider the following polynomial. And so they give us this statement of 4 minus 7ab plus 2a squared b minus b. List all the monomials. So a polynomial is just the construction of a bunch of monomials. Well, what are all those monomials in this case? We have 4, we have negative 7ab, we have 2a squared b, and then finally we have negative b. It's all the components that make up this this polynomial in this case. Now, what we should recognize is that the sign goes with each of these monomials. So if it has the negative out front, like this here and like this here, that's going to follow it into the monomial. We wouldn't just list b because that sign is attached to whatever that monomial is or whatever is behind it or directly behind. Now, list all the constants. We have to remember that constants are ones with no variables. So right away that rules out here, here, and here. The only constant term or the thing that isn't affected by a certain variable is going to be 4. So we're going to put 4 here for our constants. What is the degree of the polynomial? This may be something that you don't quite remember, but we're going to refresh it here. If you look across this whole polynomial here, this whole statement, what we want to do is we want to list the degrees of each of the monomials as a part of this polynomial. So we're going to put degree here, and then we're going to go one by one and list all the degrees. Remember, if there's nothing listed here, we have to say that the exponent or whatever's in the exponent makes up whatever our degree is. But in the first case, there isn't a variable here. It's just 4, it's just a constant. So what is our degree? We're gonna put 0 here. We then move on to our next one here, and we would see that we have AB, and AB, each of these have an exponent of 1 and 1. So the combined degree of that monomial would just be 2. So we can put 2 here. We then move on to our next one, and just like the previous example, we have a b1, a2. When we add those exponents together, we're going to get a total of 3. And then finally, we have b1, which is degree 1. Okay, so when they say what is the degree of the overall polynomial, well, the degree for this entire polynomial is defined by the highest degree. So we're just going to say that this is going to be 3. What is the leading coefficient? Well, the leading coefficient is the one that's attached to the one that determines the degree of the whole polynomial. So when we scan this and we realize that this is our highest degree, or it represents the degree of the polynomial, whatever that leading number is, or the coefficient number is, that's our leading coefficient. It's the one that leads, the one that determines our degree of the polynomial. So we can put 2 for the leading coefficient. All right, now adding and subtracting polynomials. This is a really important section because we have to realize it's all determined by the like terms, and that determines which ones come together. Now, when we add or subtract polynomials, what are we doing? We're not changing anything related to the variable or anything like that. What we're doing is we're saying what are the coefficients of each of the degrees or the different degreed variables, and then we're putting them together. So if we look in the first one, this may be a really important thing to do. We want to look at the x squared, the x terms, and the constant terms as all unique terms. So what I would do in this case is I would look down the list and organize them by maybe the x squareds get a single underline, maybe the x terms get a double underline, and then maybe the constant terms get like a squiggle. These are clearly marked differentiated terms. Now what we want to do is say, okay, we have these brackets that seem to be attached to this second piece here, but because there's an addition sign between, it's not going to flip any of the signs on the interior. It's only if there's negatives. So I'm just going to rewrite this as x squared plus 4x minus 2 plus 2x squared minus 6x plus 9, because none of those signs are going to change. We're just going to drop the brackets. Now what we have to do is use that same organization. Single underlines for the x squareds, x's get double underlines, and then our constants get a squiggle. Combining these together, we're going to find that if I take the x squared terms and I put them together, remember, anything that doesn't have a coefficient listed or an exponent listed gets a 1. So we're going to put 1 there, and we have 1x squared plus 2x squared is 3x squared. 4x minus 6x, the negatives are greater, we get negative 2x. And then negative 2 plus 9. The positives are greater in this case, so now we have positive 7. So there is our combined simplified polynomial. All right, now in sharp contrast, we're going to do very similar technique to what we just did in the last one. However, here's the big differentiation. We have a negative in the middle. The negative is going to change all the signs on the outside here. We can treat it like this is negative 1 times everything in the brackets. Remember, if there's no coefficient listed, we could just throw a 1 there because that's technically what it means. The 1 is just basically not written because it's implied it's a 1, and anything times 1 is just itself. So what we're going to do is we're going to distribute that negative 1 into all the brackets, and this is going to make us rewrite this line because the signs of those second terms are going to change. We have 4y squared minus 2y plus 3 minus 3y squared, because a negative times a positive for the negative 5y here, and then we have a negative times a negative 2, that's going to be a positive 2. Now, using the same organization that we did before, I'm going to single underline my y squareds, double underline my y's, and then squiggle my constant terms. When I combine all the coefficients together, I go 4y squared minus 3y squared is 1y squared, and realistically, I don't even need to include the 1 there, but just for the sake of the example, I will. Negative 2y minus 7 or minus 5y is negative 7y, and then positive 3 plus 2, that's going to be equal to plus 5. So there is our simplified polynomial. Now, again, do I need to include this 1? Definitely not. I could just leave that out because anything times 1 is just itself. But for the sake of this problem, I think it makes showing those coefficients really clear. All right, now one more example that involves a negative outside of brackets. What are we going to do? Right away, just put a negative 1 there, because that negative 1 gets multiplied to everything in the brackets, meaning each of those signs are going to flip. So we rewrite negative 7m squared, and I'll put an equal sign out here. We have this is equal to negative 7m squared minus 12m minus 4. Negative 1 times a negative 2m squared is positive 2m squared. We have negative 1 times negative 8y, which is positive 8y. And then finally, negative 1 times negative 2 is positive 2. Okay, let's put together our terms here. And maybe I should give a little more space here. I'm going to single underline all my m squareds, double underline the m's. Well, actually, in this case, there's a little bit of a typo here. This should actually be an m here. I'm just realizing that here, we should make this an m, or else that's just going to be an unsimplified term. So I'm going to make that an m, and then plus 2 for this outside. Now we can combine like terms, so I'm going to double underline the m's, squiggle my constants, and now when I put this all together here, I'm going to get negative 7, or I should go back here, negative 7m squared plus 2m, that's negative 5m squared. Negative 12m plus 8m, the negatives are greater, we have negative 4m. And then finally, negative 4 plus 2, the negatives are greater, so we get a negative 2. There's our simplified polynomial. Now, what we could have done is, if this isn't a typo, we would just have an 8y that's floating around, and it would just be another variable in the polynomial, which is definitely something that could happen. However, for the sake of simplifying this polynomial, I'm just going to make this an m, and then that's going to allow us to bring some terms together. All right, now multiplying and dividing polynomials, this is a little bit different. So we're now going to follow product and quotient rule and standard multiplication, standard division rules, depending on if we're dealing with coefficients or ones with variables. So whereas addition and subtraction, we're just adding and subtracting the coefficients, when we multiply and divide, what we're going to be doing is dealing with changing those exponents, just like we did in the exponents unit with product rule, quotient rule. Those things are going to change these exponents. Whereas addition and subtraction, we're not changing the exponents, we're just adding and subtracting coefficients. So let's deal with this first example here. Remember, if things are surrounded in brackets and the exponent is on the outside, the exponent gets applied to both things in the bracket. And similarly over here, the exponent gets applied to both things in the bracket, because we know that if it's included, then it gets distributed by power rule. So this is going to be equal to, we have 3 to the 3, x to the 3, multiplied by 2 squared times x. By power rule, x squared times or raised to a power of 2 becomes x to the 4, because it's 2 times 2. Okay, now let's simplify this a little more. We have 3 cubed, which is 27, x cubed, times 2 squared, which is 4, x4. By simple multiplication, what we would do is we would go, okay, we need to first multiply 27 by 4. And when we multiply 27 by 4, we get 108. And then if I multiply an x cubed by an x to the fourth power, what I'm going to do is I'm going to add their exponents by product rule. So this becomes x7. All right, now let's go on to our next example. This is going to involve quotient rule or simple division here. If I divide these terms, well, 20 over negative 60 is actually just simplifies down to negative 1/3. So I get negative 1 over 3 because 20 and 60 can both divide by 20. When I do that, I get 1/3. And then we have x squared divided by x. And remember, if there's no exponent listed there, I can just put a 1. So x squared over x1, that's going to simplify down to x to the power of 1 because it would be x squared minus 1. Or off to the side here, we could go x2 minus 1 in the exponent, which is equal to x to the 1. Now, do I need to put x to the 1? Definitely not, because anything to the power of 1 is just itself. So I could simplify this just to simply be negative x over 3. Because anytime there's a 1, that's just implied that it will give us the exact same thing back. Okay, now, for a polynomial in the numerator and a monomial in the denominator, what we can actually do here is do something that's a little bit crafty and helps us see this in a different way. We know that when we have something in the numerator divided by a common denominator, we can actually just split this up into 3 different fractions. I can split it across these signs and say this is 5m, and then 5m here, and now it's these 3 things all divided and added together. So let's start with the first one here. If I start with the first block, I'm going to say this is going to be equal to, well, 10 over 5 is equal to 2, and m3 over m1 is equal to m squared. Now we add, we're going to go to our middle term here. When I divide 5 by 5, I get 1. And so I could list 1 or just leave it. I'm going to list it here just to show that we've done it. 5 over 5 is equal to 1. M squared over m1 is equal to m1. And yet again, I don't need to really list that 1, but I will just for the sake of this example. Finally, we're going to go to our last block here and say this is adding 15 over 5, which is 3. M over m simplifies actually down to m to the 0. Now, let's actually simplify this even further. We have 2m squared plus, we don't need to write those 1s in because remember, anything to the power of 1 is itself and anything times 1 is itself. So I'm just going to put 1, or just simply m, and then plus. Here's where we need to recognize that anything to the power of 0 is always just equal to 1. Regardless of if it's infinity, negative infinity, some really large, really small number, anything to the 0 is equal to 1. So we actually get a constant term as our last piece of our simplified polynomial. All right, let's do the same thing with this last example here. I'm going to split it into 3 different sections where they're all divided by the 3r squared. Okay, we start with our first block here, or our first fraction, and we go 6 over 3 is equal to 2. R4 over R2 simplifies to r to the 2 because 4 minus 2 is 2. We then put a subtraction symbol and say 3 over 3 is equal to 1. R3 over R squared is equal to R1. And then lastly, add 9 over 3 is equal to 3. R squared over R squared is equal to r to the 0 because 2 minus 2 is equal to 0. Now, we want to do what we did in the last problem and say, well, 2r squared is going to stay the same. Anything times 1 or to the power of 1 is just itself, so I'm going to go minus r. And then we know that anything to the power of 0, regardless of if it's an r, m, z, infinity, will always be equal to just 1. So 3 times 1 is just simply 3. So there is our simplified polynomial. Now, you can do this method here like we did and separate it like that directly on the problem, or what you could do is write it as the following, which I will do in red. You could rewrite that problem and say, well, I have 6r4 over 3r squared minus, make sure that's a minus 3r cubed over 3r squared plus 9r squared over 3r squared. If you want to just take it from the problem and then rewrite it as 3 different fractions like that, that's okay. But you can also split it up like this directly on the problem, and I would completely understand what you're doing there. But if it's more visually appealing or it's easier to visualize it as the following, then definitely go that route. Okay, now distributive property. This is a big one. Distributive property implies that I have some coefficient outside of brackets and I'm going to distribute it to every term that's within the brackets. Here's what we mean. So if I take this and I realize I have some coefficient on the outside as follows and things within, I could treat this as some monomial times some polynomial or something that involves multiple variables and constants on the interior. To distribute this, what I'm going to do is take the outside term and multiply it to all three things in the bracket. This is going to be equal to 3 times 2 is simply 6. X squared times x1. Remember, anything without a power on it, we can just write in 1. X squared times x1 is x cubed because we know by product rule, we add their exponents together. Common base, different exponents, we add them together. Now, my next term, 3 times negative 7 is negative 21. X squared times y is going to be x squared times y. We can't combine those. They're just going to be multiplied together as a product. Finally, 3x squared times 2, that's going to be 3 times 2, which is 6, x squared. There we go. And then there's nothing we can really simplify from here. We can't combine like terms here. There's different powers and different variables involved. I couldn't put together the cubed and the squared. That wouldn't be right. And I couldn't put together something with a y with something with just an x. That also wouldn't make sense. So by distributive, we just need to make sure everything is multiplied into the brackets. Now, here's kind of a double whammy if you want to view it as that. We have a constant term with something in the brackets. We need to distribute, but we also need to pay attention to the idea that we have this negative here. So when I'm looking at this, I go negative 2 times 3x, negative 2 times 5. And we know that anything that involves a negative on the outside like that, what's going to happen is it's going to flip both the signs on the interior. So when we go into our next line, we're going to say this is equal to 9 minus negative 2 times 3x is negative 6x. Negative 2 times positive 5, well, a negative times a positive gives me a negative, and this is negative 10. Okay, therefore, when we put our like terms together, we realize we have a 9 and a 10 that are both constant terms. Let's put them together. 9 minus 10 is equal to negative 1 minus that 6x. And we could reorder these if we wanted. So I could put it as negative 6x minus 1. That means the exact same thing. When we look at our answers on any final exam or any type of unit test or anything in the future, typically this one is going to be the more popular route, putting them in terms of descending order of power. Now, what do I mean by that? Remember when we talked about labeling orders of power, if we look at this, we see that the x is to the power of 1. This is technically a power of 0. So if we have a power of 0 versus a power of 1, well, what does that mean? It means we want to put it in descending order of, okay, if x has the power of 1 and the other has a power of 0, or if it was like 2, 3, and 1, we'd want to reorder it such that the powers are descending or greatest to least. Okay, multiplying binomials. Binomials are things with two monomials put together. So if we see anything like these, what we're going to do is we can either use FOIL method or box method, two completely valid methods, but they do the exact same thing. By FOIL method, what are we talking about? Well, we're going to do first, outer, inner, last. Here's how that's represented, and I talked about this a lot in class, being the Pepsi symbol. We multiply our 2x to the first term, 2x to the second term. We then multiply our second to the first term, second to the last term, and it creates this kind of like double swoosh. Okay, so here's what this is going to multiply out to. If I start by multiplying the 2x times 3x, well, it's going to become 6x squared, because we know an x times an x, we add their exponents, that's 1 plus 1 is 2. 2x times 6 is going to be equal to 12x. And then now we shift to 4 times 3x, 4 times 6. Well, 4 times 3x is plus 12x, and then 4 times 6 is plus 24. Now all that's left to do is look at this and say, hey, we have two terms in the middle that are like terms. They both have just an x with coefficients. When we add them together, it's going to be 6x squared plus 24x. And then finally, plus 24 as the constant term with no variables. All right, let's do one more example of FOIL method. I'm going to do the same thing. I'm going to multiply the first to the first to the second, and then our second one to the first, second to the second. So you're taking each of the terms in the binomial and multiplying them to the opposite. Okay, this is going to be equal to 2y times 3y is 6y squared. 2y times a negative 2 becomes negative 4y because a negative times a positive gives us a negative. 3 times 3y is plus 9y. And then finally, 3 times a negative 2 gives us negative 6. Yet again, I see these two terms in the middle that I'm like, oh, those are combined like terms. When I put them together, I should get 6y squared, negative 4y plus 9y. The positives are greater than the negatives. This becomes 5y, and then minus 6. There we go. So we've expanded these brackets. When we talk about multiplying binomials together, what are we doing? We're expanding them to create some form of polynomial that's simplified. All right, now let's go over to our box method examples. Box method is very, very similar, just slightly different. What we're going to do is we're going to create a box. So you can outline just a simple square like this. You can create 4 sections or just a simple cross through it. And what we're going to do is we're going to take one binomial and list it on the left, and then one binomial and list it on the top. So I'm going to go 2x and 4. So I've put this binomial on the left, and then I'm going to put this binomial on the top. So it's going to be 3x and then 6 here. Now, what we do is we go one by one and we multiply 2x by 3x, which will give us this box here. So when I multiply 2x by 3x, I get 6x squared. I then go, okay, if I multiply 2x by 6, I would get this box here and say it is 12x. When I multiply 4 by 3x, I'll get this box, which is 12x. And then when I multiply 4 by 6, I get this box, which is equal to 24. Now our job becomes really simple because all we need to do is just pull each of these out of the box. This is going to be equal to 6x squared plus 12x, and then plus 24. Again, just like we did in our previous when we were using FOIL method, we have these two that we can put together. This is equal to 6x squared plus 24x plus 24. Now, the first thing I want you to recognize is that when we compare FOIL method to box method, we get the same answer. So whatever you're more comfortable with, if you want to FOIL, FOIL. If you want to use box method, use box method. What I will say, though, is that foiling is probably the faster method, especially because with box method, you have to set up this illustration and pull information out of it, whereas FOIL method is more algebraic mentally, and it comes together just a little bit quicker. However, they're both equal methods. Okay, let's do the same thing for our second example so that we can compare and contrast it to our first FOIL method. Okay, so we're going to create our box. We're going to create our little window here, or our cross within the box. And now we're going to assign the first binomial is going to go on the left here. And so I'm going to go, this is 2y, this is going to be equal to 3. And then I'm going to take this binomial and put it on the top. It's going to be 3y and negative 2. It is really important. If you see a negative attached to whatever number or out front of a number, you have to bring it with it, or else this will skew whatever answer you get. So when we go one by one in the box, 3y times 2y gives us this box. That's equal to 6y squared. We then go negative 2 times 2y. Well, that's going to be equal to negative 4y. If I go 3 times 3y, that gives me this box, and that's equal to 9y. And then lastly, we go 3 times negative 2 is equal to negative 6, which goes in our bottom right. Okay, piecing this together, we have 6y squared minus 4y plus 9y minus 6. When we combine our like terms in the middle here, we're going to find that we have negative 6y squared plus 5y minus 6. There is our simplified polynomial from box method. And yet again, look, we compare the two across. If I look at FOIL method, I get this answer. If I get box method, I get this answer. They're the same answer. One is just slightly quicker than the other, but both are completely valid. All right. When we go down to this example here, I want you to realize that we have a binomial that's squared. And remember from the exponents review, we said that if anything is being added or subtracted in brackets and raised to some exponent, it is not correct. This is completely not correct in red, is equal to x squared plus y squared. This is completely incorrect. this is not a valid solution. You do not want to just apply it and say, well, oh, by power rule, these go to the exponents and I'm done. No, that is completely incorrect. So what we're going to do is we're going to erase that. We're going to now do the correct solution, which is to say, if I have anything squared, let's say it's x squared. Well, x squared when it's separated is x times x. It means we write it out twice. X plus y times x plus y. Okay, now we have a binomial times a binomial. Just like we did before, we can do FOIL or box. I'm going to use FOIL method. So I'm going to multiply the first to the second two, first to the last two. This is going to be equal to x times x, which is x squared, x times y, which is x times y times x, which is x times y again, and then finally y times y, which is y squared. What you'll realize is when you use FOIL method or box method, you're going to have these two in the middle that you can put together. This is equal to x squared plus. The coefficient on both of these is technically 1. You have 1xy and 1xy that comes together to be 2xy plus y squared. So there is your simplified trinomial, or three monomials coming together to make a trinomial. All right, now we have a binomial times a trinomial, or a two-term polynomial times a three-term polynomial. What do we do here? Well, if we use FOIL method, it actually gives us the same answer. However, what we could do is use box method as a way to do this. I'll explain the FOIL method. The FOIL method is simply this. First gets multiplied to all of the next three, and then the second term gets multiplied to all three. So technically, what are you doing? You're just multiplying by one more term. Okay, if I do box method for this example, what I'm going to do is set up a box such that I have, whoops, that gave me a weird shape there. I'm going to put a box here. And now we need to realize that we have a binomial. So I'm going to split it in half by a trinomial, which means I'm going to have 3 slots in the top. So if I take my first binomial and I put it off to the side, I'm going to have x and then -5. Remember that negative has to go with it. You then have x squared plus 3x, and then finally -4. Okay, if we multiply this through, we're going to get x times x squared, which is x cubed. We then go x times 3x, which is going to give us 3x squared. And then we're going to go -4 times x is going to give us this box, and that's -4x. I then move on to the bottom row. We have -5 times -x squared, or times x squared, which gives us -5x squared. I then multiply 3x by -5x. That's going to give me -15x. And then lastly, -4 times a -5 is going to give me a +20. Okay, now we want to list all these things out together. So I'm going to go below here because this is actually a quite large expansion. I'm going to say this is equal to x cubed plus 3x squared minus 5x squared minus 4x minus 15x plus 20. Okay, now it's important to go one by one and really categorize what terms you have, because when we add or subtract, it really matters. If I have x squareds or x cubes or constant terms, what do I have? So I have 1x cubed. I have these 2x squared terms. I have 2x regular x terms, and then lastly I have a constant term out here. So do you see how I differentiated all those different terms so that I can combine them? I use single underline for one thing, double underline for another, triple for another, and then like a squiggle for the constant or whatever you want to do here. So when I combine the like terms here, I'm going to get x cubed. Positive 3x squared minus 5x squared gives me -2x squared. -4x minus 15x squared gives me -19x. And then lastly, the constant is the only constant there. So we just go +20, and there is our simplified polynomial. So remember, if you have 3 or more terms such as this, in this case we have 4 terms, we just simply call this a polynomial. It doesn't have a certain prefix. It's not like binomial, trinomial. There's not a specific term. When it gets to be 4 or more, we just call them polynomials. So this is an example of a polynomial or a bunch of monomials coming together. All right, now determine the area of the shaded region. This is a really popular one for unit tests or certain quizzes that you may see in the future. When you deal with these type of problems, what they're trying to get you to do is realize that you need to do 2 simple multiplications and then subtract those from one another. So what we're going to do is realize that the entire area of the box is represented by the multiplication or the product of these two regions, because we know that we say, or those two lengths and widths, because we know that if I multiply length by width, that's going to give me area of whatever rectangle. So of the entire rectangle, we know it's the multiplication of 3x plus 2 times 2x plus 5. Because we could consider this as the length, we could consider this as the width, and so this is length times width, which should give us that area. And then we're going to do the exact same thing with the second one here. We're going to go length times width, or specifically, we're going to subtract this away because it's a hole in this square. We're going to subtract away the product of the length times width, which is x, let's erase that, x plus 1 times 2x. And this was technically our length times our width. And this was area of the whole rectangle minus area of the small rectangle, which removes that little hole, and that would give us the area of the shaded region. Now, what we're going to do is binomial times binomial. We can FOIL this. So I'm going to FOIL this by multiplying 3x times 2x, which is going to give me equal to 6x squared. I'm then going to go 3x times 5, which is going to give me plus 15x. I'm then going to multiply 2 times 2x, which is going to give me plus 4x. And then lastly, I'm going to take this and multiply 2 times 5, which is equal to plus 10. Now, this is all subtracting away whatever we get for the second expansion here. When I multiply, and I'm going to include this in brackets because we do have that minus there, so I'm going to put brackets. When we multiply this, we go 2x times x is 2x squared. We then have 2x times 1 is plus 2x. Now, remember when we did our previous expansions and we saw this negative lingering out front here, what we have to do is multiply it in, because we know that coefficient is technically -1. So that's going to change the signs of both of these. This is equal to 6x squared. I'm going to combine my x terms here. 15 plus 4 is plus 19x plus 10. And then now we're going to distribute this. -1 times a 2x squared is equal to -2x squared. We're going to multiply in -1 to positive 2x, which is going to give me -2x. And then now my last step is just to combine the like terms. My x squareds are going to get a single underline. My x terms are going to get a double underline. And then my constant is going to get like a squiggle. Okay, so the area of the shaded, so I'm going to call it this, area that's shaded, is equal to, and maybe I should have done that above here too, area is equal to, and we go down, area of the shaded, it is equal to 16x squared minus 2x squared is 4x squared. 19x minus 2x is equal to plus 17x. And then the constant that's available is just plus 10. There's nothing to combine that with. So there is the area of the shaded region. We take the larger rectangle or the whole rectangle and subtract away that little hole or that gap, and that's going to give us whatever the shaded region is. It's represented by this trinomial, or three monomials coming together here. All right. Factoring. This is a really important skill that goes into 10C, and we need to be really aware of this. If I factor, what that means is I'm going to take out a GCF. When I factor, I'm typically saying, what is the GCF? That's my first thing I'm always thinking about, because before I can do any more factoring, I have to, or before I do factoring and I pull it apart into its two components or two or more components, it has to always consider a GCF. So with this type of problem right away, we're going to factor by looking at it and saying, what is the greatest amount of n's that we can pull away from both of these? Well, the greatest amount of n's I can pull away from both of these is 2. So I'm going to put n squared out front, and then I'm going to put in brackets. When we pull an n squared out front, what are we technically doing? We're taking this and dividing each of them by the n squared. So if I divide both of these by an n squared, well, n squared over n squared gives me n to the 0, which is technically just 1. And then n5 over n squared is going to leave me with n cubed. So that's all I can factor from here. I've removed everything I can. We're done there. All right, I go to my second problem, and I'm going to do the same thing. I'm thinking about a GCF. Step 1 is always to remove a greatest common factor. Well, what can 3x squared and -6 both be divided by? they can both be divided by 3. So if I divide both by 3 and put that 3 out front, that's going to leave me with 3 divided by 3 is 1, which leaves just the x squared. And negative 6 divided by 3 is negative 2. There we go. There's my fully factored form right there. So some of these problems, when they say factor, might just simply be pull out a GCF and then stop there. All right, now we look at this. This looks like another GCF problem. We're just going to see what is the largest amount of x's and what is the largest number we can remove from all these that represents a GCF. So what I'm going to do is I'm going to figure out what can 12, 8, and 4 all divide by? Well, they can all divide by 4. And then what is the largest amount of x's that can be removed from all of these? It would be x squared, because they at least all share x squared. Okay, when I divide these all by 4x squared, and 4x squared becomes the GCF I put outside the brackets, well, 12x4 divided by 4x squared is going to leave me with 3x squared, because 12 divided by 4 is 3, and x4 divided by x2 by quotient rule simplifies to x squared. Negative 8 divided by 4 is negative 2. X cubed divided by x squared by quotient is equal to x1. And then finally, 4x squared divided by 4x squared, that's the same thing. Or 4 divided by 4 is 1, and x squared divided by x squared gives you x0. This is simply just equal to 1, but maybe I'll show that in the step here. So 4 divided by 4 is 1, x squared divided by x squared is x0. And now, to really simplify this, we have 4x squared, 3x squared, minus, and then on the outside here, we're going to say that this is 2x plus 1. There we go. And I should say on the inside, by the way. Okay, so we've removed out a GCF. That's all we can do. We can't progress with this anymore. Now, we could potentially look on the interior here and say, okay, well, this represents some form of trinomial that could be factored further because we see that squared term here. But I'm going to leave it at that just because in 15, we didn't do a lot of we basically did no work with coefficients of x squared that were greater than 1. We only had a couple of those, but they were challengers. So I'm not really going to dive into factoring these. I'm just going to leave it at that. All right, going to the second problem. Remember, this was when we factored by parts. So if we had got it to this point here, well, we look at this and we'd say, okay, both of these share a common factor of x plus 1. This is like me writing something like this, x times z plus 3 times z. If it represents the same thing, well, we could simplify this and say this is going to be equal to z out front, which is the greatest common factor, times x plus 3. Same concept is here, but instead we just have a binomial that we can factor out as our GCF. So our GCF here is represented by the x plus 1, which I could formalize below. GCF is equal to x plus 1. When we remove the x plus 1 out front, what are the two things that we're left behind with? Well, the one thing we're left behind with is x. The other thing we're left behind with here is our plus 3. So there is our factored form here. All right, going down to this example here, if we look down the line here, what we're going to do is we're going to factor this by pairing them and then pull out some greatest common factor and continue from there. So if you remember from class, what we did is we put our first two together and our second two together. This is factor by pairing. And so when I pair the first two together and I remove out a greatest common factor, well, they each share x squared. So I'm going to pull out x squared, leaving behind an x1 plus 1, because we know that if I divide each of these by x squared or take out a GCF, that's going to leave me with x and x plus 1. This is adding. When I look at the second pairing, well, the greatest common factor that's shared between these two is going to be equal to 3. So I put 3, leaving behind x plus 1, because I am essentially dividing both of these by 3. Now what I recognize is that from the previous problem, we recognize we have this GCF or a factor that's shared between the two. If I pull that out front, the x plus 1 that is shared between the two out front, what is left behind? It is the x squared and the 3. So this becomes x squared plus 3, and there is our factored form. All right, similar to the last problem, what we're going to do is pair these and then simplify it. So I pair the first two, pair the second two, And anytime you see this type of situation where it's 4 terms or a polynomial of 4 terms and they say factor, you should immediately be thinking pair these together. Okay, of the first pairing, what is my GCF? Well, 2 and 6 both share 2, so I'm going to remove 2 out front. And out of x cubed and x squared, they at least share x squared, so I'm going to remove that out front. If I take a 2 and an x squared off of 2x cubed, I get x left behind. And then if I take -6 and divide it by 2, or take, -6 divided by 2, I would simply get -3. X squared divided by x squared, or if I take an x squared off of this, it's just leaving me with that. And then now, with this next one, what is a greatest common factor I can take off of x minus 3? Well, they at least share 1 together. So what I can do is actually just write +1 and then leave it exactly how it is. Now, I recognize that I have this common factor between the two of them, so I'm going to place that common bracket out front, x minus 3. What am I left behind with? 2x squared plus 1. So I'm going to go 2x squared plus 1 in their own bracket. You take whatever's the shared thing, put it out front, so you can see that we took this x minus 3, it's shared, and thus we put it out front, and then we just put our two things remaining in their own bracket together. And that represents our factored form. All right, evaluate and express your answer with algebra tiles and with a polynomial. Okay, so they give us the tiles here. Remember that shaded represents a positive and then unshaded represents a negative. So if I was to write this above, what I technically have here is rectangles are represented by x, and since it's shaded, it's positive. The single little squares are representative of 1, so I have 1 and 1, and then a -1 because it's unshaded. And then I have an x on the left-hand side here, a -x because it's an unshaded rectangle, and then 2 individual ones because they're both shaded. Now, what we have to do is do what we did exactly with the box method, but now we're just doing it with tiles. So if I go x times x, that gives me a certain thing here. That's going to be a fully shaded cube representing an x squared. So I could fully shade this, and maybe I'll do that first and then right above it. So this is representative of x squared. We then go our x times 1, which is going to give us a solid or shaded x term. We do that again for this one because we go x times the 1 will give us this one. And then finally, if I go -1 times x, well, what is that going to give me? That's going to give me a -x term, so it's an unshaded rectangle. Okay, now we move on to the next row. X times a -x, this is an unshaded square. It's an unshaded x squared. Reason being is because we go -x times a positive x, that's a -x squared. And we continue down the line and say -x times 1 is a -x. -x times 1 is a -x. And then -x times 1, well, a -1 times a -x gives me a positive x. So this is going to be shaded here. Okay, now I continue down into the last row. X times 1 is going to give me equal to x, which is shaded. I then go x times 1, which is just a positive x again. And then now I do all my 1's together. 1 times 1 is going to give me a positive 1. 1 times 1 gives me another positive 1, and we do that another 2 times because it's 1 times 1 for these two as well. And then lastly, we have to do our last two spots, -1 times 1 and 1. That's going to give us 2 -1s or 2 unshaded ones. Okay, let's put this all together in terms of a polynomial because we did them all in terms of shading and unshading, and now this is a completed multiplied polynomial, but now we have to put it all together in terms of the actual equation or the actual polynomial. So this is going to be equal to, we have 1 positive x squared, 1 negative x squared, we have 4 shaded rectangles which represent x's, we have 3 unshaded x's which are the negatives. We then have, or I should say we have 5 x terms actually, so I'm going to put a 5 here. And then we have 4 1's that are positive and 2 negative ones which are unshaded. Okay, we put this all together to represent the polynomial. X squared minus x squared, those go away. These eliminate down to 0. They're the same thing. So we have no x squareds. 5x minus 3x is 2x. 4 minus 2 is equal to positive 2. So our reduced polynomial in this case is equal to 2x plus 2, and that represents this polynomial coming together here. Okay, factor trinomials. Factor the following expressions completely. Well, remember, when we factor these, there's a certain method that we can do. And now your method might, or your organization might look a little different. I'll show the two that I represented in class, but yours still might look a little different. If I want to factor this, what I have to realize is that I have to multiply to make the outside number, add to make the middle. So what I mean by this is I'm going to write it out like this. We have to multiply to make some outside number. In this case, it is 1 times 6. Well, 1 times 6 is equal to 6. And we have to add to make the middle coefficient, which the middle coefficient is 5. So two numbers that multiply to make 6 and add to make 5, well, I would say that's 2 and 3. 2 and 3, there we go. So because our coefficient of the x squared is equal to 1, when a is equal to 1, we can just directly go into our factored form. We do not have to do decomposition. So our factored form is equal to x plus 2 and then x plus 3, and we're done. Now, in order to show this, that this is actually the trinomial, or this is the factored form for the trinomial, you could reverse this. Binomial times binomial, or foiling or box method, you could go in the reverse direction from here to confirm that. However, we don't really need to do that in this case. Now, if I wanted to show another method is to draw an x and say what multiplies to make the outside number, adds to make the middle. That would be 2 and 3. So we could also represent it using this x pattern. Maybe I'll do the x pattern on the second one just to make it clear. So if I need to multiply to make a number and add to make a number, well, I know I have to multiply to make 1 times 12, which is equal to 12. And then I have to add to make the middle number. Remember, take the sign of that coefficient, it's negative 13. Okay, if I have to multiply to make 12 and then add to make negative 13, well, what I could do is say that this is going to be equal to negative 12 and negative 1. When I multiply those two things together, I get a positive 12. When I add them together, I get a negative 13. So this is definitely correct. And we could say that the factored form is x minus 12 and then x minus 1. All right, here's where things get a little bit different. If I have a coefficient where a is not equal to 1, this is a really important thing when we multiply this. And I've shown it on the last two examples, but let's just make this really clear. I draw my x here. What do I have to multiply to in this case? It is the coefficient a times the last number. So a times the constant gives me what I have to multiply to. Well, if I go 3 times 3, that's equal to, we have to multiply to make 9, add to make the middle, which is negative 6. Okay, if I have to multiply to make a positive 9, add to make a negative 6, I'm going to put negative 3 and 3. When I multiply negative 3 times negative 3, that gives me a positive 9. And when I add them together, I get negative 6. So this seems to add up. But here's the big thing. When a does not equal 1, we must use decomposition. As soon as you see that a does not equal 1, we must use decomposition. It is not correct to just go, oh, the factors are equal to x minus 3 times x minus 3. That would be completely incorrect in this case. What we have to do is now rewrite it as this. 3x squared minus, now we put in our two found numbers, negative 3x minus 3x plus 9, or plus 3 I should say, because that was our constant term. Now, one thing you should recognize right away is that negative 6 is equal to negative 3 minus 3, or negative 3x minus 3x. That's the same thing. We've just split it apart into the two numbers. Now, I'm going to pair this, so I'm going to pair the first two, pair the last two. What is my GCF for the first one? Well, I can remove out a 3x from both of them, leaving me with x minus 1. And then of my second one, I never want to have a negative just left here. So what I'm going to do is pull out the negative with it. It's going to be negative, and then whatever they share, in this case, they share a factor of 3. But what I recognize is that when I remove that negative, it's going to make the first term positive and the second term negative. Because I took the negative off, I took this negative and removed it out front. When you remove it out front, you're taking it out, meaning whatever the first term would be positive, second term would then become negative if this is a positive. Okay, now we're at the point where we have two shared brackets that can be a GCF. That x minus 1 is a shared GCF, or greatest common factor, between the two sets of numbers here. And then what are we left behind with? The part that's left behind is our 3x minus 3. And so we get 3x minus 3. There we go. There is our factored form. And you can clearly see that's a lot different than simply just saying x minus 3 times x minus 3, which would be slightly incorrect here. Now, one thing we could even do that's a little bit further here is we could remove out a factor of 3 from this one. So this would be like above and beyond if you wanted to go there. We could say this is 3 times x minus 1 times x minus 1, which then becomes 3 times x minus 1 squared, because we're multiplying two of the same thing together. What I've done here is I've said if these things both share 3, I'll just take that 3 and remove it out front. And when I remove it out front, I get x minus 1, and two things that are the same become one thing squared. So that would be above and beyond. If you wanted to go on to that step, that's okay. But if you got to the step here, that would also be considered factored as well. So it depends on what the answer looks like, but most likely that's going to be okay. Okay, by inspection. Inspection means that the coefficient of A is 1. So when they say by inspection, this means A is equal to 1, which we can clearly see in all these examples here. If you go down this entire list, the coefficient of x squared is 1. Now, when they say inspection, that just means we need to figure out what multiplies to make the number, adds to make the middle number, and then figure out what those two factors are. So two numbers that multiply to make 15, or negative 15, I should say, and then add to make 14 in the middle. Well, if we look at that, two numbers that multiply to make 15 would be things like 15 and 1, 3 and 5. But the only things that are going to add in this case to positive 14 would be negative 15, or x minus 15, and x plus 1. And I guess these should be opposite because we need to add to make a positive 14. So I'm going to go 15 and then x minus 1. And if I expanded that back out, I could get the same thing. Okay, now this is equal to, we're going to go to the next one, multiplies to make negative 15, adds to make negative 14. So this is going to become x minus 15 and then x plus 1. So we're just going to reverse them because now the 14 has to be negative. We go on to our next one. This is going to be multiplies to make 21, adds to make negative 10. Well, things that multiply to make 21 are things like 3 and 7 or 21 and 1. So what we're going to do is we're going to say because 7 and 3 are the only things that can add to that, well, x, and because it has to be positive, we're going to have x minus 7 and x minus 3. They both have to be negative in order to multiply to make a positive. In the next one, we want to multiply to make a positive 21, add to make positive 10. That means we're going to do x plus 7 and x plus 3. Okay, we move on to the next two. We're going to have where we have to multiply to make negative 30, add to make 7. Well, things that multiply to make 30 are things like 5 and 6, 10 and 7, or not 10 and 7, but 3 and 10. So if we go down the list, we'd realize 10 and 3 are going to be the right answer. Now, it must be that x plus 10 and x minus 3 are the two factors because 10 minus 3 is 7 and 10 times a negative 3 is 30. Now, they both have to be negative, so it's going to be multiply to make negative 30, add to make negative 7. That means we're going to have x minus 10 and x plus 3. They're just going to flip places there. Okay, and then the last two, we're going to say that we need to multiply to make negative 36, add to make negative 9. So the two numbers that are going to do this for me, well, if I have to multiply to make 36, we know 6 and 6 does that. We know 8 and 4 does that. Or not 8 and 4 in this case. We know 9 and 4 do that. And then finally, we know 12 and 3 do that as well. So what I can do here is say that if 12 and 3 are going to be the solution, we have to multiply to make negative 36 and add to make negative 9. It must be that x minus 12 and x plus 3 are the solution here. Because if I add together negative 12 and positive 3, I get negative 9. And then lastly, we have the same factors, but we just need to reverse the order. Plus 12 and then x minus 3. There we go. Because 12 minus 3 will give us 9, but 12 times a negative 3 gives us negative 36. All right, and then for our last two problems here, this one's pretty open-ended because there's multiple answers that would make this true. We just need to conceptually understand what's happening in this problem. So they say, what values of k would make this expression factorable? Meaning that I can split it into two factors or I can pull out a GCF, but in this case, because it's a trinomial, I want to make it sure that it can split into two factors of some kind, and this will work. So k could be really a bunch of numbers, but we're going to figure out a couple of those. So when we do our standard factoring, we know that it has to multiply to make some number and then add to make some number. So in the case of our trinomial over here, x squared minus 7x plus k, we must multiply to make 1 times k, and 1 times k would equal to just k, and then we have to add to make the middle term and its sign, which is -7. Okay, so two things that will multiply to make -7, or multiply to make k and then add to make -7. Well, things that add to make -7 would be things like -6, and I'm going to do this all below in an ordered list. We have -6, and then times, whoops, let me go back here. Things that add there we go. Now we have our ordered list here. So things that add to make -7, well, we have -6 plus -1. We have maybe -4 and -3. We have things like -5 and then plus a -2 would also work. What would another one be potentially? We have 6, 1, 4, 3, 5, 2. Pretty sure that covers the most of them. Now, here's what we can realize about this is that, well, I guess we could even go more of these. So what I'm doing is I'm thinking about all the ones that are under 7. What we also could do is say things like -10 plus a +3. Well, that also equals that. And we could generate infinite combinations here. We could say -11 plus 4 in this case would also give us -7. And we could continue on and on and on. And this would all give us factors. So there's really an infinite amount of combinations that make this work. And that's what's a little bit tough with these. Now, when they multiply to k, here's what happens. We're going to take all those same numbers, or the ones that we generated at least, and we're just going to multiply them together. -6 times -1 is equal to 7. Or is equal to 6, my bad. Then we go -4 times -3 is equal to 12. And then we go -5 times -2 is equal to 10. Then we go -10 times a +3 is equal to -30. And then we go finally -11 times 4, which is equal to -44. Now, here's what I want you to realize is that look at how many already possibilities there are for k. So k could really be any of these solutions here. K could be equal to 6, 12, 10, -30, -44, and on and on and on. It could potentially be way more solutions than that, but that's the ones that we came up with. So they say, what values of k make this expression factorable? Well, we could probably come up with many more, but in most cases, you'll just need to be able to provide maybe one or two just to show that it is factorable. Or if it's a multiple choice question, just at least one or two that would match up with the solution. All right, and then lastly, what values of k would make the expression x squared plus kx minus 9 factorable? This is the same kind of concept, but just slightly different. What we need to be doing now is saying it's going to multiply to make 9, but then add to make k. So we're going to say it multiplies to make -9, but then adds to make k. Now, this one, there's not really infinite combinations with this one because when you deal with sum you can typically come up with a bunch of different numbers, really large, really small, that would add to make a certain number. But when it comes to multiplying, there's only a certain amount for this. So we want to multiply, first of all, multiply to -9. Okay, when we multiply to make -9, well, the things that would do that would be things like -9 times 1. That definitely equals -9. We could do -3 times 3. This would also equal to -9. And then realistically, I think that's about it, because multiplying to make -9, there's not really any other things we can do. 3s are it, and 9 and 1 are it. What we could do is, I guess we could flip the signs of these. So we could say 9 times a -1 would also give us -9, and that 3 times a -3 gives us -9, but that's basically the same thing. So realistically, the only options we have are these three here, with this one just being basically a repeat. So I'll almost put it in blue here just to isolate it. Now, we know it has to add to make k, or that middle number, so add to make k. And so when we add these numbers, -9 plus 1 is equal to -8. We have -3 plus 3 is equal to 0. And then we have 9 plus a -1, which is equal to +8. So our options, therefore k, if I was to say therefore k can equal ±8 and 0. If you're unfamiliar with this symbol, when we put the plus and minus directly above and below each other, what that's saying is that it can be either or. It could be +8 or -8. It could also be 0. So there's our possibilities. Now, you can clearly see when we multiply, there's a lot fewer options. We can only realistically multiply to some number really only in a specific amount of ways. It's not infinite. Whereas when we're adding to make a number such that we're adding to make, or we're multiplying to make some, when we're adding to make some number in the middle and it's given, we can come up with a bunch of different combinations here. So just realize that, yeah, if you're given this type of equation where k is the multiplied number, you're typically going to have a bunch of options there. Whereas when k is the middle number and we have to add to it, there's going to be a lot less options here.